Hey guys, it's Miss Taryn. I'm here to go over the notes we missed today because it can get pretty involved. So if you weren't here, this is to go over what you missed today. All right, so today we talked about the conservation of momentum in collisions. So with conservation of momentum, it's just saying that when we have a system of objects that aren't influenced by things like friction, the total momentum cannot change. So we saw that in the Science of Football video the other day, where the momentum before is equal to the momentum after. So if you're on roller skates or a skateboard and you have a basketball and you throw it forwards, then you're going to go backwards. Oops. Let's see, how do I get... There we go. All right, so the formula for this is pretty lengthy. It looks kind of scary, I know. But when we break it down, it's really not as bad as it looks. So, for example, m1v1. So we have mass times velocity. All right, so that's what we've been learning. It just means momentum. So it just means momentum. The P, so P means momentum, because P, momentum equals mass times velocity. So the 1 indicates that, we have 2 items in a collision. We need to have at least 2 things. The 1 just means the first object. Remember when we talked about velocity earlier, we talked about initial and final velocity. That's all the I and F means. So what this equation boils down to mean is that the momentum of object 1 at the beginning plus the momentum of object 2 at the beginning is going to be equal to the momentum of object 1 at the end plus the momentum of object 2 at the end. That's all it boils down to. It's just momentum of object 1, the momentum of object 2, and that's before. So our initial momentum, and then we have our momentum at the end. Remember, F means final. Is going to be equal to our final momentum. That's all that equation is saying. So not as scary as it might look. All right. So again, our total initial is equal to our total final. All right, so I have a practice problem. 2 skaters are standing motionless, are facing each other in the middle of a skating rink. One has a mass of 91 kilograms and the other has a mass of 57 kilograms. The skaters put their palms against each other and push off. The heavier skater is moving to the right at 0.75 meters per second. What is the velocity of the second skater who is moving to the left? And we're going to ignore friction. All right, I find when we have these types of problems, like we're going to be having today and for the next few days, I find it easier to take my notes in a T-chart. So, I'm going to draw a little T-chart. Kind of sorry about skater 1. Oh, I can't really read that. Let's see if I can get it clear. So skater 1 and skater 2. It says that they are motionless facing each other at the middle of the skating rink. So that means their initial velocities are 0. So V1I equals 0. V2I equals 0. One has a mass of 91 kilograms and the other has a mass of 57. So mass of 1 equals 91 and mass of 2 equals 57. These skaters, let me see here. The heavier skater is moving to the right, so the final velocity is the heavier skater, so that's going to be skater number 1. So the skater number 1's final velocity, so V1F, equals 0.75. And it wants us to calculate the final velocity of skater number 2. All right. So We're going to use our formula to help do this. So m1v1 plus m2v2 equals, might have to, all right, see if I can get some more space somewhere. m2v2 equals m1v1 final plus m2v2 final. All right, if we pop in our numbers, that's going to give us 91 times our velocity, initial velocity, which is 0, plus m2, which was 57, times its initial velocity of 0, equals, all right, now we're going to look at our final ones, 91 times 0.75 plus 57 VF. All right, so smaller with. All right, so 91 times 0 is 0. Plus 57 times 0 is 0. Equals 91 times 0.75. 91 times 0.75 equals 68.25. Plus 57 VF. All right, so this now at this point is an algebra problem. Our VF is essentially our x. So now we got to isolate our variable. So what we're going to do is we're going to subtract 68.25 from both sides. So it becomes negative 68.25 equals 57 VF. Now, to keep isolating, we got to divide by 57. Divide by 57. And that's going to end up equaling negative 1.2 meters per second. All right. So that ends up being our final velocity as skater number 2. All right, moving on. So collisions occur when two or more objects hit each other. So during a collision, momentum is transferred from one object to another. It can be elastic or inelastic. So elastic means that when these two spheres meet, they are going to bounce off one another and they maintain their shape. However, with inelastic, when they run into each other, they're not going to maintain shape. They're going to kind of join together and then move with a common velocity in the direction of the greater velocity. So again, elastic is when they bounce off of each other. So when you're playing pool and you hit your cue ball and it goes and hits the one ball and you're trying to get them into the pockets, you're counting on the bouncing. So that's going to be a elastic collision. Inelastic collision are when objects stick to each other after collision, like our football players. This one is colliding with the ball carrier to try to get him down and get the ball stopped. That's inelastic. All right, we have a chart here. You can go ahead and fill it in on your paper. All right, so with inelastic and elastic, so with inelastic, two objects stick together. With elastic, they collide and then return to the original shape. With inelastic, they move with a common velocity after colliding, but with the elastic, they move in separate directions. In both of them, momentum is conserved. With inelastic, kinetic energy is not conserved, but with elastic it is. And then you have one more, mechanical energy converted to thermal energy. With inelastic, you're going to have a blank spot on your paper for the other one. All right, the formulas. Here's the formulas for both of them. So we saw this one on elastic. We saw that one earlier. It's the same as the conservation of momentum. So we have our momentum of 1 initial plus the momentum of 2 initial equals the momentum of 1 final plus the momentum of 2 final. So we see that one again. Now, if you notice, is there an undo button? I don't think there is. Right here, let's open the highlight. This is the same as down there. Our difference here is that with an elastic we combine. So if we see here, we have a combined mass and a combined velocity, which gives us a combined momentum. All right, so we're going to look at an inelastic collision problem. A train car moving to the right at 10 meters per second collides with a parked train car. Okay, they stick together and roll along the track. If the moving car has a mass of 8,000 kilograms and the parked car has a mass of 2,000 kilograms, what is their combined velocity after the collision? All right, so again, we're going to do a T-chart. If you give me a second, I'm going to move it to the next screen. I'm just writing down. The story isn't on the next page. So I'm just going to go ahead and write my notes on my own paper real quick. So mass 1, 2. That way I can change the screen and we won't lose our information. All right. So we have our formula. You can see the answer there, but you'll see how we get there in just a second. We're going to start with our T-chart. So we have, I'm going to change the font color. We have the moving car and the parked car. The mass of the moving car was 8,000. I can't really see that too well, can you? All right, so I'm just going to label down here. That's mass of 1, mass of 2. And then our velocity, initial velocity of 1. The initial velocity here was 0 because it's parked. And we want to know the final. All right, so we're going to write down our formula. M1 V1, that's the initial, plus M2 V2 initial equals M1 plus M2 times VF. All right, so I'm going to plug in my numbers. So I have 8,000 times 10 plus 2,000 times 0 equals 8,000 plus 2,000 VF. So 8,000 times 10 is 80,000. Oops. $2,000 times 0 is 0. Equals 8,000 plus 2,000 is 10,000 VF. All right, we got to get our variable, which is our VF alone. So we're going to divide both sides by 10,000. Divide both sides by 10,000. And that gives us a final velocity of 8 meters per second. And since it's positive, we're going to the right. All right. Just kind of looking through there. So that was the formula. All right, so next to last slide. So momentum changes when a net force is applied. So the inverse, the opposite, is also true. If we have a change in momentum, we have a force being created. All right, if the momentum changes quickly, large forces are involved. So remember, if we have a small t, we're going to have a big force. But if we have a big T, like a big amount of time, we're going to have a small force. So again, that's why like we have the airbags in the car, because it helps change the impact of the accident by increasing the amount of time that it happens, and that would thereby decreases the force. All right, the impulse momentum theorem. In a collision, an object experiences a force for a specific amount of time that results in a change in momentum. The result of the force acting for the given amount of time is that the object's should be velocity here, so please correct that on your paper. The object's velocity either speeds up, slows down, or changes direction. What do we call that? We call that acceleration. Woohoo, acceleration. The impulse experienced by the object equals the change in momentum of the object. So in equation form, force times time equals mass times velocity. So that's just saying that our change in momentum, or triangle means change, is going to be equal to our impulse. They are equal to each other. So sometimes you'll have a problem that might ask for the time or something else, and you will have to set these two equations opposite of each other to calculate for that answer. All right, so in a collision, objects experience an impulse. The impulse causes and is equal to the change in momentum. All right, that's it for today's notes. Make sure if you need more help, you come to tutoring or let me know somehow, and we'll see what we can do to help you out. Otherwise, have a great day.